We know from Ohm's law that I is equal to V by R. V is nothing but the voltage in the circuit and R is the resistance. Junction rule is very simple and very obvious. Kirchhoff stated that if I amount of current is entering into a junction, then I amount of current should exit from that junction. So it will be having three resistors, one at the top end, one at the middle end, and finally there is one small resistance between the battery, that is small r, which indicates internal resistance. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were discussing about Ohm's law and its factors. Now it's up to step the game and we will be discussing about batteries and currents. So let's begin. So cells. What are exactly cells? We have learned about cells in biology, but for a physicist, this is exactly what is known as a cell. You might have seen these connected to circuits. So this symbol is actually for a cell. And when two cells comes together, we can say that it's a battery. So this particular symbol indicates a cell. So what exactly is a cell? So cell is basically essentially a battery. That is, if you go to a store and buy a battery, then you will get something like this, where this will be the positive terminal and this will be the negative terminal. So you will have a positive terminal and a negative terminal. When you connect this to anything, let's say for a circuit connected to a bulb, then this bulb will glow. So what exactly is happening here? So cells, inside the cell, what is actually there? We know that energy can neither be created nor be destroyed. So what exactly happens inside the cell is that energy, that is chemical energy, is being converted into electrical energy, and that particular electrical energy is traveling into the bulb where it is converted into heat and light energy, and it travels back into the cell. That is, let's say if this battery has a 5-volt potential difference. Why it is 5 volt and will it be different when it is connected to a circuit? Everything will be discussed shortly. So let's say you went to the store and you bought a 5 volt battery and then immediately you connected that to a circuit. So my question is, what exactly is inside a battery? How does it function? So what a battery does is that it will push all the small electrons inside this circuit so that the electrons run around through the circuit, powering this little light bulb, and finally it will go back into the battery, completing the circuit. So the battery here is a power source which pushes electron or which provides that potential difference so that the circuit is being completed. But what is inside that particular battery? We can see a similar setup for a battery that you have seen in electrochemistry. That is, if you have a beaker, let's say this is a beaker filled with H2SO4 solution. That is, this is H2SO4 solution, and if I keep two electrodes, let's say these are two electrodes, one being zinc and the other being copper. So if I keep two electrodes like this, one being zinc and one being copper, then obviously there will be an exchange of ions inside this particular solution, because you have seen this in electrochemistry also. That is, this setup is also used for electroplating. So what exactly is happening here? Obviously it is the exchange of ions. That is, atoms will become ions and ions will be deposited, or the exchange of ions will be happening inside this particular case. So this particular ions, for example, if here it is, let's say SO4 minus ions, and let's say there are H plus ions, the point we are aiming for is that these particular materials or these particular ions are charged particles, which means that in current electricity, it does not matter if it's a solid, if it's a liquid, if it's a gaseous matter. The only thing we are concerned about is that there is a charge, which means that there will be flow of charges in this particular solution, which means that it can generate electricity. So this is a photovoltaic cell. So the symbol, that is this particular symbol for a voltage source, let's say for a 1 volt source, is actually this particular one. If I connect a resistor in between these two, let's say of R, then effectively it is the same diagram as this one, because the cell is this particular one and resistance R is being connected in between them. And we can say that this photovoltaic cell roughly will generate a voltage of 0.96 to 1. Generally, it will generate a voltage of 1 volts. So why are we discussing about this particular cell? That is because we are going to identify what are the differences that may arise in connecting this particular cell or this particular battery into a circuit. Will it have any effect when the circuit is opened or closed? That is, when current is flowing through the circuit and when the current is not flowing through the circuit, is there any difference to this particular battery arrangement, or this particular cell is affected by the current flow? We are going to inspect that right now. Obviously, we know that there is going to be an ion exchange between these two electrodes completing the circuit through this electrolytic solution, where the SO4 minus ion atoms are the one which are completing the circuit. That is, this SO4 minus ions will complete the circuit, causing a bridge. It can be plus ions or minus ions. The point is that this electrolytic solution is the one completing the circuit. So charges or ions, when they are traveling, let's say the electric current is traveling through this particular circuit, completing the circuit. Once they reach this end, they have to swim across this electrolytic solution in order to complete the circuit. And it will be comparatively difficult for ions to cross over this particular electrolytic solution compared to this circuit. So keep those 2 points in mind. As we tread even more further, it will be useful. So the question was very simple, right? Is there going to be any difference for a battery which is connected to an appliance when the circuit is closed and when the circuit is open? So this is a battery connected to a circuit through a switch or a key. I'm going to switch it on, then the circuit is closed and current flow will be there. If the switch is open, then there is no current flow. So let's say this is resistance R. It represents anything you have connected to a circuit using that particular battery. It can be your phone, it can be your toaster, it can be even your hairdryer. So whatever it is connected to a battery. So let's say I went to the store and purchased a 50 volt battery, or let's say for simplicity's sakes, it is a 5 volt battery source. It is written that it is 5 volts. But when I measured it in the store using, let's say, a voltmeter, I measured what is the potential difference across each ends. That is, this is end A and this is end B. So when I placed a voltmeter across the two ends, I got the reading 5 volts. So this battery is exactly 5 volts. Fine, I am satisfied. So I went back to my lab, connected all these equipments and switched on the switch. That is, now the circuit is closed. So current flow is happening and this particular resistance is getting a decent amount of current flowing through that particular resistor. But when I measured the voltage difference between these two circuits or these 2 points in the circuits using a voltmeter now, I was shocked. The voltage actually decreased. So why was this happening? Is there any difference when the voltage source or the battery is being connected to this particular circuit? That is what we are going to investigate. So scientists actually find out, people actually investigated about this and they found out that even inside the battery, when the circuit is being switched on or when the circuit is actually complete, then inside the battery there is a small amount of resistance still occurring. That is, inside the battery there is a small resistance, that is small r. So it is not just a resistance provided by the wire or any equipment that is being connected. It is not just the capital R, but inside the battery, when the circuit is switched on, there is a small amount of resistance within the battery through which the circuit or the electrons have to flow through and deal with. So this particular small resistance is known as internal resistance. That is the resistance which is within the battery or within the cell. This particular resistance is known as internal resistance. For the cell which I showed you, that galvanic cell which had the positive and negative electrodes, that particular internal resistance was nothing but the electrolytic solution through which the ions had to swim through and complete the circuit. For this particular battery, this is the internal resistance, and this is being represented by small r. So now coming to the point, why the difference between voltages inside the battery, that is when it is connected and it is disconnected to any appliances. So for that, we have two different distinct names. Obviously, the voltage will decrease because the power is coming from the cell. That is why the voltage drop happens. But why? But what is it scientifically known and why that happens is being discussed here. So EMF, what exactly is EMF? EMF is defined as electromotive force. Electromotive force. This actually is not a force. Why it is named is because of historical significance and small mistakes in the history. Just know that this is not an actual force. It is basically just essentially voltage. That is, this is basically just voltage, but it is not the voltage which you encounter inside a circuit when it is connected to power. That is why we represent EMF with a curled E. That is, a curled E is used to represent EMF. Basically, it is voltage, but it is not exactly the voltage we talk in our daily life. Why? Because EMF is defined as, it is defined as the potential difference between the positive and negative electrodes of a cell when the circuit is open. It is very important that when you define a cell in terms of EMF, we are saying that it is in an open circuit. That is, the switch is off. The circuit is open, it is not closed. So there is no current flow within the circuit. No current is taken from the battery so that the circuit is open, and that particular voltage of that particular cell is known as EMF or electromotive force, which is actually not a force, but the voltage of that, the potential difference between the two electrodes, that is between the positive end and the negative end, is known as EMF. If you're buying a battery from the store which says it has 5 volts, then if you measure the battery, that is between the positive and negative ends, you'll get 5 volts. That is known as the EMF of the cell. Now, what do you call when you connect this particular battery or cell to a circuit? Then obviously current will be flowing through that. That is why we bought the cell. So when the current is flowing through that, because of the internal resistance present, the voltage will actually decrease. This particular decrease in voltage, or this particular state where the voltage is applied in a connected circuit, is known as terminal voltage. So the normal voltage which we discuss in our physics labs and physics textbooks is known as terminal voltage, and that is the one indicated by the letter V, and that particular voltage is defined as potential difference between positive and negative electrodes when the circuit is closed, or when there is current flow within the circuit, we can say that that will be the effective terminal velocity. That will be the effective terminal voltage of that particular cell. That is, in this case, this is terminal voltage because the connection is closed. Current is flowing through this particular resistor. So we can say the voltage being supplied is known as terminal voltage. And you must also note that between these cells, that is between these electrodes, there is a small r within that. That particular r, or that particular small r, is known as internal resistance that arises due to what is within the battery. So when the electrons have to swim through that electrolytic solution, or in the case of a modern day battery, that particular material which is inside the battery, if it's lithium ion, then lithium ion. If it's depending on the battery you're using, there will be internal resistance depending on the material which is inside that particular cell. So that resistance is known as internal resistance, and we are now going to consider that also. So internal resistance is denoted by small r, and it is defined as the resistance offered by the electrolytic solution, because we were dealing in terms of electrolytes. So if this is H2SO4, then this will be zinc and this will be copper, the electrolytic setup, which is a galvanic cell right now. And then we can say that this particular cell, the internal resistance for this particular cell, the internal resistance R is offered by the electrolytic solution inside that particular cell. So it is known as internal resistance of this particular cell. So the electrolyte offers a finite resistance, and that small resistance is known as internal resistance, small r. So for now we discussed about what is voltage. So now we discussed about what is terminal voltage, what is EMF, and what is internal resistance. That is, we discussed about curled up E, terminal voltage V, and internal resistance R. Now how are these quantities related? So the relationship between internal resistance, terminal voltage, and EMF of a cell is being explained right now. We know from Ohm's law that I is equal to V by R. V is nothing but the voltage in the circuit and R is the resistance. But for now, if we take a circuit, let's say this is the circuit, then this particular cell is now denoted in terms of EMF, because we just learned about it. So this is EMF E of that particular cell, and there is a small r, that is resistance, internal resistance between those two electrodes, and that is denoted by small r, and there is a capital R which offers a large amount of resistance in that particular circuit, basically whatever you're connecting that battery to. So we can write this particular equation as E, that is the EMF of the cell divided by the total resistance in that particular circuit. So the total resistance is that capital R and small r. These are connected in series. So capital R plus small r. So R plus R. Just so you don't forget, if resistors are connected in series, they add up. R1 plus R. If they are connected parallelly, then it will be, if they are connected, let's say if they are connected parallelly, R1 and R, then we can write it as 1 by R plus 1 by R1. That will give you the effective resistance. Just so you don't forget about it, you have learned it in your PU first year. So the effective resistance in this particular circuit can be written as R plus small r, the main resistance plus the internal resistance. So we have an equation that is I into R plus R is equal to curled up E, that is EMF of the cell. Or we can simply write it as IR plus I into small r is equal to epsilon. So we have two equations relating curled up E, that is EMF, and current running through a circuit. So it will be the summation of small resistance and internal resistance times the current running through that circuit. It is basically Ohm's law written in terms of EMF and internal resistance. And just so there is no doubt, we can I told you that when the circuit is closed, then the voltage of that particular battery drops. That is, if initially it had a 5-volt capacity, when the battery is connected to a circuit, and if you are observing that, then we can say that the battery dropped down to, let's say, 4.5 volts. That is the operating voltage of that particular battery is 4.5 volts. So why the drop? That is because if epsilon is the net EMF of that particular cell, then V, that is terminal voltage, will be equal to epsilon minus IR. When the circuit is open, there is no resistance being offered. That is why we measure it as EMF. When the circuit is complete, it has to travel the entire distance, which means that the internal resistance offered by the battery also comes into play. So that is why there is a dip in the voltage measured. So terminal voltage can also be represented by this particular formula, which states that the EMF of the cell will drop when it is connected to a circuit, and that drop will be equal to the product of current times internal resistance offered by that particular cell. So that is why terminal voltage will be less than the actual EMF of the cell, just so you don't have any doubts. So you can note this also down. Here, this particular V is nothing but terminal voltage. So V is equal to epsilon minus IR. You have three equations, both are very important. So just note it down. Now, since we have discussed about cells and how they function, it is time to introduce these cells into active circuits. Cells being connected to resistors which are more than one in number, and there are more than one loop in that particular system. That is, in this particular network, we were dealing with a simple circuit which had only one small resistor connected to a small circuit. But now we are going to step up the game, and we are going to introduce multiple circuits which contain many number of resistances and many EMFs connected. For now, let's increase the number of resistors being connected and create a circuit. So let's say for now, this is our particular circuit which will be having an EMF of E and an internal resistance of R. Don't forget about the internal resistance right now. And then it is connected to a resistor which is capital R1 and then capital R2 and R3. Now, we know that how they are connected in series, the resistances add up, that is all known. But we are going to deal with something new here, and that something new is known as Kirchhoff's rule. What exactly is Kirchhoff's rule? So Kirchhoff's rule, Kirchhoff or Kirchhoff's, however you want to pronounce it, that rule is regarding the electric current or the voltage flowing through that particular circuit. So we know that when the circuit is closed, terminal voltage will be present in the circuit. So current will be flowing through this particular circuit. But how will the current be flowing? Just like water in a pipe, you might have an overhead tank. Imagine that this is a pipe in your building. Let's say this is your building. And this is a pipe at the very end of the building. So there is a huge water tank at the top of your building. Even though there are many houses in there, there is only one tank. And that tank is very huge, having a huge capacity. which means that all the water will be stored in that particular tank, and then water will be distributed to each of the houses inside this particular flat using pipes. And one particular pipeline is connected to a tap which is outside the building also, which means that it is the same water that is flowing from this particular tank to each of these houses and the tap which is being kept outside. Just like this, there is only one battery source here. There is only one cell connected to that circuit, but the current flowing through this circuit will be same, but it will be split. That is, just like how the water is split coming from the, just like how the water coming from the tank is split into different areas of the houses or different houses and to different taps, just like that, this particular current, that is, let's say this is I amount of current flowing out from this particular cell, then when it reaches this junction, let's say this is A, this is B, this is C, D, E and F. So the circuit is closed. So when the current reaches the junction A, it is posed with a problem. He is standing in front of a junction. That is, there is a right and there is a straight path. Where do I go? Unlike us, current can actually split. So what will happen is that if I amount of current is reaching the junction and it is presented with two opportunities to go, then the current will split itself, and let's say I1 amount of current will go through R1 resistance, while I2 current will be flowing through the R2 and R3 resistances or resistors. So current reaching this particular junction will split into I1 and I2. And afterwards, just like this water, let's say after all this, the pipeline connects itself to the end of the pipe. All the houses, the pipelines are connected through one single network, which means that if you trace it back, it should reach the water tank itself. Just like that, it will be the same water reaching the water tank. We can say that as all the amount of current which is entering and or being split into each of these junctions will rejoin at the other end. So when it reaches the other end, that is D junction, or when it reaches the point D, they will combine together at junction D to become I again and complete the circuit by going into the negative terminal of the battery. So as it starts from F, it goes to A, it splits up into I1 and I2, and as it reaches the junction D, it becomes whole again. That is, I will be equal to I1 plus I2. Always I amount of current is coming from the EMF of the cell, and then I amount of current is going back to this particular cell. So there is no magically disappearance of current in this particular network, which is closed. That is very important. This particular circuit is closed. There are no leaks, there are no gaps. Current is not escaping anywhere. So it is being run around in this particular closed circuit. And this was actually studied by a scientist, and that particular scientist is Kirchhoff, and his rules are known as Kirchhoff's rules or Kirchhoff rules, however you want to pronounce it. And they are of two. Kirchhoff has two rules. One is junction rule and one is loop rule. So loop rule is also known as voltage rule. So let's dive right into junction rule. So Kirchhoff's first rule, that is junction rule. Junction rule is very simple and very obvious. Kirchhoff stated that if I amount of current is entering into a junction, then I amount of current should exit from that junction. All the current entering into a junction should exit from that junction. It is like saying that in a heavy traffic, all the cars coming into a junction will have to exit from the junction. So, for example, we can actually say that if there is current entering into this particular junction, let's say I1 and I2 current is entering into this particular junction, let's call it as A, and current is leaving into three particular terminals. Let's say this is I1 and I2 are entering into a junction, and output is three ways. I told you current can split. So let's say I have connected three different wires to this particular junction. Then I'll call these connections I3, I4 and I5. That is current exiting from that junction. Then Kirchhoff's junction rule states that all the current entering into that particular junction should exit from that particular junction, which means that I1 plus I2 will and should be equal to I3 plus I4 plus I5. And this is nothing but Kirchhoff's junction rule. This is junction rule. This is junction rule. All the current entering into a junction will exit from that junction, which means that if I amount of current is entering, I amount of current will be leaving the junction, which means that net current in that particular system will be zero. This is junction rule. That is the first rule said by Kirchhoff's. And secondly, Kirchhoff mentioned one more rule which we already discussed actually. That is known as the voltage rule or the loop rule. So we are going to discuss about loop rule or the voltage rule. We already seen in the second chapter that if it is a closed circuit, then that is, if it's a closed circuit, then the electric field in that particular juncture will be zero. Electric field or E dot dl is nothing but voltage. That is from the relation minus dV by dr is equal to E. So from this relation we can say that E dot dl for a closed surface is equal to zero. You don't have to study this. This is just how the physics works behind this rule. I just wanted to let you know that this is the physics working behind this particular concept. So we don't want to make things complicated. So simply we can say that loop rule says that the net voltage in a particular loop will be equal to the sum of product of current and resistors in that particular circuit, which is equal to the EMF in that particular loop. That is, loop rule states that in a closed circuit, which is very important, in a closed circuit, algebraic sum of product of current and resistance will be equal to the total EMF in the circuit. So, in a closed circuit, the sum of product of current and resistance will be equal to the total EMF inside the circuit. That is, basically we are saying that voltage or EMF will be equal to I times R or capital R, whatever it is, it will be equal to the sum of currents and resistance inside that particular loop. So we can see an example for that. So consider this particular circuit A, B, C, D, E, F, A. So why back to A? Because it is a closed circuit. So it will be having 3 resistors, one at the top end, one at the middle end, and finally there is one small resistance between the battery, that is small r, which indicates internal resistance. It's not technically a battery, it's a cell which has an EMF of curled up E, but usually we say battery. So anyways, what loop rule actually suggests is that the voltage, if we take one particular loop, that is A, C, D, F, A, or B, C, D, E, B, or A, B, E, F, A, any one of these 3 loops we take, in each individual loop, the current and resistance multiplied together will be equal to the EMF in that particular loop. So let's see one example. I am taking the loop which is B, C, D, F, B. So B, C, D, F, B. I am taking this particular loop. So let's say that in this particular loop, what will be the net current or what will be the flow of current in that particular loop. Before that, we must identify where the current splits. So we know that I amount of current will be coming out of this cell, and then at the junction it will be split up into I1 and I2, which means that I1 will be flowing in this direction and I2 will be flowing in this direction. This will play a crucial role very soon, because I2 amount of current will be flowing first through R2 resistance and then later on to R3 resistance, which means that I2 R2 plus I2 R3. So this much current is flowing through these 2 resistances together, and we must complete the loop. So when I2 is traveling through R2 and then through R3 and finally it is reaching the junction D to E, and then it is taking a turn so that it can complete the loop, because we are taking this loop. So it is coming back here and it should go through R1. But there is only one problem. R1, already one current is going through that is I1. So we don't have to take I2 current flowing through that particular R1 resistance. We are going to take I1 current which is flowing through that particular circuit. But here there is one small problem. Here we have taken the loop in this clockwise direction, which means that we are traveling through here, going through here, coming here, and then coming back. But the current flow, that is I1, is flowing in the opposite direction of the loop we are taking. The direction is opposite to that. If we assume that I2 is flowing in this clockwise direction, I1 is flowing in the opposite direction of that. Just because of that, we have to consider that this is going to be a negative sign. So I1 R1 will be negative. The amount of current flowing through that particular resistance R1 will be negative because it is in the opposite direction of the loop we are taking. What does the loop rule state? It states that I2 R2 plus I2 R3 minus I1 R1 will be equal to the EMF in that particular circuit. Is there any battery in this particular closed circuit? No, there is no battery connected in that particular loop, which means that this will be equal to 0. So this is loop rule applied for loop number 1. Now we have 2 more loops. So the second loop is A, B, E, F, A. So this is the second loop. Again, I'm going along with the battery, the natural conventional flow of current I'm following. So first, I current is flowing here, and when it reaches junction B, it splits into I1 and I2. So I1 R1. Right now, I1 R1. I1 current is flowing through R1 resistor, and then when it reaches junction E, we must also note that this I1 and I2 combines together, that is, this I2 and I1 is coming together at junction E, which means that the current that is coming out of junction E is I1 plus I2, which is equal to I. So even though I1 R1 is flowing through this particular resistor, here I1 current and I2 current combines together and reverts back to the I current which is flowing through this particular junction. Why this is important is because there is not only one resistor here. There is another resistance in the form of internal resistance. So we have to take that also into account. So the current flowing through this particular resistance is nothing but I small letter r, and the signs are positive because we are taking the clockwise direction and no current is flowing against our against the direction which we have taken. So we can say that both are positive. I1 R1 I1 current is flowing through R1 and I amount of current is flowing through the internal resistance, which will be equal to the EMF of that particular cell, which is E, because there is a battery present here. So this will be the equation for the loop ABEFA, a closed loop. And now for the third and final loop, that is ACDFA. So ACDFA. So here again, I current is coming here. It is splitting into I2 and I1. And since we are taking the outermost loop, we can say that I2 current is flowing through R2. So I2 R2 plus I2 R3. I1 and I2 combines together to form I, which means that it is IR amount of current flowing through the EMF of the battery. And there is only one cell in the circuit. And this will be the equation for the third loop. So this is how we find current, resistance and voltage relation in each of these particular cases. So this is also known as voltage rule because again we are finding the net voltage in a loop. So this is known as a voltage rule also. So together the junction rule and the loop rule or voltage rule together makes Kirchhoff's rules. So know that loop rule is nothing but the voltage rule, that is calculating the net voltage in a particular loop, and you know the definition. And for the junction rule, it is basically the amount of current entering into a junction will be equal to the amount of current exiting from that junction. That is known as junction rule. Given that in both these cases the circuit is closed. I hope you have understood about Kirchhoff's rules, cells, EMF and all the funs that come along with that. In the next class or in the next session, we'll be learning about an applicational field in the Kirchhoff's rule, that is Wheatstone's bridge. So until then, I'll see you all very soon. Thank you.